Welcome to the Technology Addicts podcast. In this episode, we'll be diving into an article from the latest issue of Focus magazine, exploring the fascinating world of the all-electric society. Welcome to the Technology Addicts podcast. In this episode, we asked our experts to address the 10 most frequently asked questions about automation in the all-electric society. 1. What are the challenges of integrating automation into legacy energy infrastructure? Many existing energy systems are based on proprietary technology that has limited compatibility with current communication standards. This poses a significant challenge to automation integration. A lack of standardized interfaces for sensors, data transmission, or remote maintenance further complicates the process. Outdated control systems and a lack of documentation also make retrofitting difficult. Safety requirements and ongoing operation also restrict interventions. Modernization, therefore, often requires bespoke solutions and considerable technical effort. These factors, combined with the challenges of compatibility, data silos, and cybersecurity risks inherent in legacy infrastructure, make modernization a complex and resource-intensive undertaking. 2. How will industrial automation be influenced by the all-electric society? The growing demand for energy efficiency and flexibility is driving the adoption of intelligent, networked automation that align with the principles of the all-electric society. Industrial digitalization provides the standardized data space that enables cross-manufacturer data exchange between components or systems. This standardization opens new avenues for sector coupling, particularly concerning end-to-end value chains and networked systems, fostering greater adaptability and responsiveness to market demands. Local DC grids for industrial production facilities are also important. The direct current generated by renewable energy sources can directly supply grid consumers, such as machines, motors, and conveyor belts, reducing conversion losses. Thanks to networking in the DC grid, it is also possible to feed a system's breaking energy back into the grid as electricity, potentially saving up to 10% of energy. This approach not only boosts efficiency, but also contributes to a more sustainable and resource-conscious industrial landscape, which are key tenets of the all-electric society. 3. What are the cybersecurity risks of automation in energy systems, and how can they be mitigated? Connecting control systems, sensors, and cloud services creates new potential attack vectors for hackers. Risks can arise from unsecured communication protocols, outdated software, or insufficient access controls, making systems vulnerable to unauthorized access, data breaches, or operational disruptions. To mitigate these risks, strategies such as network segmentation, regular software and firmware updates, strong encryption, and adherence to established security standards like IEC 62443 are essential. Legal requirements for cybersecurity and critical infrastructure have been in place for some time, and the EU's new NIS2, Network and Information Security Directive, further expands these obligations. Meeting the stringent requirements of the NIS2 directive is only possible if products are developed with a security-by-design approach from the outset. To support this, the EU has introduced the Cyber Resilience Act, which aims to ensure that digital products and services are secure throughout their lifecycle. 4. What challenges and requirements does edge computing place on power supply modules? Edge computing brings processing power closer to machines and sensors, which places significant demands on power supply modules. These must be compact and highly energy efficient to fit within space-constrained environments while minimizing energy consumption. Robustness against environmental influences, such as temperature extremes, humidity, and vibration, is essential, especially in industrial settings. Voltage stability, EMC compatibility, and strong temperature resistance are particularly critical to ensure reliable operation. Additional challenges include accommodating limited installation space, managing high power density, and providing an uninterruptible power supply for continuous operation. As edge deployments grow, intelligent power supply modules with advanced monitoring, diagnostic, and remote management capabilities are increasingly necessary. These features enable real-time oversight, fault detection, and performance optimization, supporting the reliability and efficiency required for edge computing in demanding environments. 5. How can automation support the transition to electric mobility in the all-electric society? Automation plays a key role in the success of e-mobility. Intelligent systems control the charging infrastructure in line with demand, stabilizing the grid by enabling load management, prioritization, and time-shifted charging to prevent grid overloads. These automated systems can also integrate electric vehicles into the power grid as mobile storage units, facilitating technology that allows electric vehicles to supply energy back to the grid. This enables bidirectional charging, further contributing to grid stabilization and resilience. However, realizing the full potential of this integration requires standardized interfaces, robust data management, and stringent cybersecurity measures to ensure secure and reliable operation. 6. What standards exist for miniaturized connectors that require edge computing solutions in the all-electric society? Key standards for miniaturized connectors in edge computing include the IEC 61076 series, which covers both industrial circular and rectangular connectors, and the M8 and M12 standards, known for their compact design and suitability for signal and data transmission. The IEC 63171 standard defines single-pair Ethernet and is also frequently employed for high-speed data transmission in space-constrained applications. These standards facilitate robust, space-efficient connections, which are particularly crucial in challenging environments. Standardized requirements such as EMC protection, vibration resistance, and IP protection classes further ensure the reliability and durability of these connectors. 7. By what percentage can the volume of data to be transmitted be reduced by sensors with Edge AI capabilities? Sensors with Edge AI capabilities can substantially reduce the volume of data that needs to be transmitted, often by 70% to 95%, and in some cases even up to 99%, by processing data locally and transmitting only relevant results, for example, anomalies, trends, or alerts. Edge AI minimizes unnecessary data transfer. This significant reduction lowers bandwidth usage, reduces latency, and improves overall system efficiency. 8. What do Edge AI capabilities mean for a sensor's energy consumption? While adding more computing power to sensors, Edge AI inherently requires more energy. It doesn't necessarily translate to higher overall energy consumption. The key here is that pre-processing data at the edge significantly reduces the amount of data that needs to be transmitted, potentially lowering overall energy consumption by a substantial margin, sometimes up to 90%. Modern energy-saving AI chips, such as those used in tiny ML, neural processing units, and edge tensor processing units, further optimize energy consumption. Consequently, for battery-operated sensors, Edge AI is often more energy efficient than the continuous data transmission required by non-intelligent sensors. 9. Which operating mode is optimal for my smart home or smart building application? Hybrid control elements offer an ideal balance of flexibility and ease of use for smart home and smart building applications. These systems combine touchscreens with physical buttons to provide users the benefits of both approaches. Touchscreens provide flexible visual control, while physical buttons provide fast, intuitive operation best suited for frequent functions such as lighting or blinds. Touch panels provide a comprehensive overview and scene control, while physical buttons offer haptic feedback and enhanced reliability. Voice control and mobile apps are also useful additions to the system and provide further convenience and accessibility. Ultimately, user-friendliness, accessibility for all occupants, and seamless system integration are the most important factors in determining the optimal control strategy. 10. Can the same circuit breakers be used in the DC network as in the conventional AC network? DC networks require particularly fast and intelligent switching devices in order to protect neighboring DC sectors in the event of faults such as short circuits or earth faults. In contrast to AC systems, where the current is zeroed 100 times per second and thus enables safe disconnection, the current zero point must be actively generated with direct current. In addition, the fault current in DC systems increases extremely quickly due to many capacitances, up to several tens of amperes per microsecond. These dynamics and the rapidly falling voltage require ultra-fast protective devices. Traditional mechanical circuit breakers with switch-off times measured in milliseconds are generally unsuitable for DC applications. Instead, DC networks require circuit breakers specifically designed for fast and reliable interruption of direct current. Thank you for tuning in to this episode of the Technology Addicts podcast. For more exciting episodes, be sure to follow us on your favorite podcast platform and make sure to check out the show notes.